Alrighty, we're going to do carbon NMR. It'll be a nice short video because carbon NMR is thankfully much easier than proton NMR is. Now, carbon NMR is different in that we have to use carbon-13. Remember that in order for to look at resonance of a particular nucleus, it needs to have an odd mass number. We know that about 99% of carbon is carbon-12, right? Which does not resonate. And so we're looking at only 13, carbon-13. And so about 1% of carbon is carbon-13, and we have a smaller percent that's carbon-14, right? But carbon-13 is the only active nucleus here. And so as a result, it's actually much harder to acquire a carbon-13 NMR spectrum because we just don't have as much of it, right? And what's nice about this is that we know that protons, they split nearby protons, right? And we don't see that carbons splitting hydrogens, we don't see nitrogens, we don't see oxygens, because most of these not even heteroatoms, the carbon, nitrogen, and oxygen, most of those have even mass numbers, so they are not NMR active. But carbon-13 is. And so we don't see, it's not going to be split by other carbons or heteroatoms. And because there are often so many different hydrogens that can split it, we can actually decouple that from the rest of the spectrum, which is pretty cool. Technology, basically, it allows us to decouple splitting done by hydrogens. And so what's interesting with this is that all carbons peaks show up as singlets. There are ways to make them have splitting, but typically you're just looking at singlets for everything. And so that makes it easy. We also see that the integrations are also not relevant for us for a couple of reasons. Just because of the way that these are acquired using the Fourier transform and this decoupling, we don't get reliable integrations. We also see that the baseline for these is going to be pretty noisy. So we're going to see that carbon NMR spectra are going to be kind of like, see all this noise down here? There's not a flat baseline. We just have singlets showing up at various places. And so no splitting, no integrations. So the only thing we have left is chemical shift, and that's the only thing we look at in carbon NMR, which is awesome. It's the only what's the term? Usable. For generally speaking, there are some advanced techniques that more modern instruments have, which are pretty cool, that give us more information. But unfortunately, those are not covered by ACS, so I will mention them, but your problems that you'll have will not have these advanced techniques for carbon NMR. So all we have is chemical shift. All right, so a carbon NMR spectrum usually goes from about 0 to 220 ppm. So different range, right? And we're going to see that around between 150 to 220, I mean, I'll even say the carbonyls are going to show up definitely way at this end. So aldehydes and ketones are way up at 220. You have your other COs around 200, 190, 180, thereabouts. Between 150 and 170-ish, you have aromatics, aromatic carbons, or double bonded carbons. Those all show up around 150 to 170, thereabouts. So thereabouts, give or take. And the next region, I forgot 100 on here, didn't I? Between, I mean, that's kind of also within the purview of the aromatic range. So maybe 130 to 170 thereabout is where you're going to see aromatics and double bonded carbons. Usually around 100 or so, 175 thereabouts, 80 is where you see carbons bound to halogens, single bonds to oxygens, heteroatoms, triple bonds. Those all show up between 50 and 100 thereabouts. And then down here, CH, plain old simple sp3. sp3-CH bonds show up between 0 and 50. So a lot easier than proton NMR, right? We only have a very few flavors of carbon. We have plain old CH for sp3 carbon, 0 to 50, 20, 30, that's normal. We have our sp carbons as well as heteroatoms next to carbons between 50 and 100. Then between about 130 to 170, we have our aromatics. And then above that, we have carbonyls. And that's it. Ta-da! That's all we need for carbon NMR. Excuse me. So when we're looking at these, just like before, the number of signals depends on symmetry. So if you have something like this, you're probably going to see 3 signals. Probably, right? Because of symmetry. You'll see 1, 2, 3. We're looking at carbons this time. So you'll probably see 3 signals with that. And you'll see that this one will be about 220. This one probably around 50, and that one's going to be like maybe 20 or so ppm. So somewhere around there is what we're looking at. And so it's all about the symmetry, just like before. And it's really just kind of, it's a supplement to proton NMR, right? Something like this, you'll see probably 2 signals only. In proton NMR, you'd see a singlet worth 3 hydrogens, or worth 18 hydrogens, I guess. We'll only see one thing. Singlet of 18 hydrogens, and it will be around like 2.0-ish, thereabouts. In carbon NMR, you'd see 2 peaks. You'd see one at about maybe 150, and then another maybe at like 40. You'll see 2 signals. So carbon NMR can tell you if you have a benzene that's fully substituted, because the proton NMR just shows you 2 ppm. It's not aromatic, right? Aromatics show up at 7. But aromatic hydrogens, we have no aromatic hydrogens here, but we do have aromatic carbons. And so you'll see those in carbon NMR. So there are places where you'll see things that you would not see in proton NMR, but you would see in carbon. Of course, with a molecule like this, you'd probably be able to deduce from the molecular formula that you have a benzene in there. But it's a supplement of information. So, it can help you decide if you have an aldehyde or a ketone versus a different carbonyl a little bit better than IR will. However, aldehydes are very distinct on proton NMR. You see that lovely aldehyde peak at 9 or 10 or so, and it's always a singlet. I don't want to say always. Usually is a singlet unless you have some weird long range coupling happening, but weirdness happens. You're not going to see that on my exam. I think some of the Tomasi problems, that's the problems that I gave y'all. That one, there may be some long range coupling, but typically you won't see that. So carbon NMR is a good supplement to proton NMR. Still valuable information to be had there. And the symmetry works the same way. Chemically equivalent carbons will show up at the same space. So in this particular molecule, we have two different types of carbon, and whereas we only have one type of hydrogen in this molecule. So just keep that in mind. It's a good supplement to NMR, proton NMR. So just a little bit of help. So this is where you're going to see things, and it's a good kind of check for you. You say, I've got aromatic ones, or I've got vinyl ones. It's a good way to tell if you have that, even if you don't have hydrogens on those. If you have something like, whatever, something like this, you're not going to see any vinyl hydrogens because there are none. You won't see anything at 5 to 6 or so. You're not going to see any hydrogens there because there aren't any. You're only going to see hydrogens at lower, more upfield regions. And so as a result, carbon NMR will tell you, you've got two carbons there, somewhere around 150 or so. That'll indicate your double bond. All right, so good stuff there. All right, I'll tell you about the cool techniques. Adept, or dept, as it's sometimes called. Adept is automatic. Dept is depolarized. I don't remember what the acronym stands for. But it's a pretty cool technique because it allows you to see different things. You'll get several spectrum at different angles taken, and you'll see that you'll have just the kind of regular proton decoupled carbon NMR. You'll have the depth at 90 degrees. And you'll see the depth at 135 degrees. These are different angles that measurements are taken at, and you don't need to know about them, but what's really cool is you'll see that different numbers of hydrogens will show up at differently in these. So in regular, you'll see regular peaks. And for these, I'm going to draw them as actual peaks because you'll see what's going to happen with the next one. So with the depth 90, you only see methine hydrogens. You do not see anything for the others. You only see CHs because they're the only ones that are going to show up at a 90-degree angle. Don't worry about why. Just accept it. So the different detectors placed at different angles just will receive different signals. And so putting those together lets you just see CHs separately. And at 135, what's interesting is you'll see anything with a hydrogen, but CH2s go upside down. You get upside down peaks for CH2s, for methylenes. And you do not see regular or quaternary carbons. So as a result, you can tell how many hydrogens each carbon type has, because it'll show you, regular one shows you all of them. 90 degrees shows you CH only. Depth, the 135 will show you CH3s and CHs normally. So by comparing 90 and 135, you can tell if something has 1 hydrogen or 3. CH2s will be upside down. And if something is showing up with a regular but not in either of the depth ones, then it's a quaternary carbon. So it's very useful information. Although this is not something that we're going to see on, it's not like right now required by ACS, so sorry. So it's a cool thing. It's more information, which is great. And what ADAPT does is it actually will just it'll take all this information and combine it into one spectrum, and it'll color your peaks different colors. Like it'll have one color for CH3s, one color for CH2s, one color for CHs, and one color for just quaternary carbons. And wow, did I spell regular with 2 G's and nobody told me anything? Well, I guess I'm not doing this live, so regular with 1 G. We'll show you all of them, right? So that's what we're going to be looking at in our examples. We'll see regular carbon-13. Unless I decide to be very nice and give you extra information, but it's not necessary. You don't need it. It's helpful, but it's not necessary. So the ACS has decided it's not a fundamental part of the curriculum. There's also some cool bits. You can do heteronuclear NMR, correlation spectroscopy, which takes a proton NMR spectrum and a carbon NMR spectrum and lines them up for you, and you see where things line up, like which carbon and which hydrogens things line up. It's pretty cool. But that's not something that's also covered. That's more advanced NMR, so we don't deal with that. All right, so that's carbon NMR. Let's take a look at a couple of examples. What do I have here? Let's see. I realize this cut off, and I don't know where. But I wanted to show you a couple more examples. Here's benzaldehyde carbon NMR up here. I'm on Chegg. Go figure, my turn. Benzaldehyde, so it's got an aldehyde group, which is what we see here, about 205, 210 or so. And then we have the rest of the aromatic carbons down here. And then proton NMR, you see the lovely aldehyde hydrogen, and then you've got some aromatic ones here. Notice the scale here. We don't have any aliphatic hydrogens, so they're not indicated here. And so there we have it. You can see it again. Nothing down here at a low range. Stuff only higher up. All right, so that's carbon NMR. We've done it. Hooray. Get to work. Work on your practice sets. Label all these, and we'll have a good time. All right, good luck.